Okay, continue with the way Matlab handles programs. Last class, what we did is basically I showed to you how to create small samples, small programs that simply calls another program to do specific tasks and return some results into here, some values into here. And this one here is basically the one that responds to the command window. Okay, so what we're going to do now is something a little more complex. It's a very simple example that can be easily understood by you. And this is going to be also part of your third assignment. Let me show you Matlab. I will provide you with these programs. Okay, I will provide you something that is called Census data analysis. And this program is a toy program that I created with the example we have been working in class that has, remember, age, gender. So it's going to be 0 if male, 1 if female, and 3 years of education. Okay, so it's a very simple construct. And the construct, as soon as we don't have an input here or an output here, everything is going to be developed in this program. This is also a good review for your data array skills. Okay, so I created the values. So X are going to be basically, we have 10 individuals. Let's take a look to this. So X has 10 individuals. These are the ages of each of them, and this is female or male. That's all. Right? And then what this program is doing, guys, is using a program that is going to help us with gender selection. So we create another program that is called gender selector, so we can see here. And gender selector needs 2 inputs, needs the data and needs the gender that you need to input. And then it will create, as we have been doing, the find command, looking at the data and returning only the males. Males or females, depending on what you select. So if you want to select, so what you do is you input the X is going to be the data, this one here. 0 is men or males, and 1 is females, right? So here what you're doing, guys, is calling from this program called Census Data Analysis, calling another program that is called Gender Selection, and Gender Selection is going to basically provide you with all the rows that corresponds to all males, all the rows that corresponds to females. And the same happens when we create a drink selector. Remember that the variable of interest here is the age. And then we have created age selector that is, it uses some if. You can use the way we have been doing before, but if you want, you can use the if, else, and then that we're going to discuss this later, and etc. So, and here what I've done also, I have added another data set we created artificially that corresponds to the number of educations. And then what I'm doing here is I'm joining X with Y. And then several questions here, and I created another program that is called Educator or Edu Selector. And then you can take a look at these programs, how they work. Okay, so one thing here is that I put here a D, okay, and this D is any random letter. The way I suggest you to run the program is click and make appear the red button, run, and it will stop here. And then you can be checking all the results, understanding how this works, etc. Right? So this is going to be basically, you need to understand how this works. You need to play with this. And after that, what we are going to be doing, or what you are going to be doing, is you need to solve the assignment number 3. What is the assignment here? This is the third assignment. Okay, so this is the program that will provide you with all the subroutines. You need to just replace the values and see if this works and test it. And then you have another program that you need to create that should be called my linear equation, and you just follow the instructions here. It's also very simple M-file, a very simple program. I will provide you then all this material to you. Now what we need to start working with, and this is going to be the topic of this class, is going to be basically working with matrix algebra. Okay, so we're going to start understanding matrices, how they work, etc., and doing a lot of examples, special matrices, etc. Okay, so let's clean my command window. And let's start working very simple linear algebra that is going to be helping us to understand how Matlab works and how we are going to be working on our financial economic problems. So there are some special matrices, guys, that, for example, I will call matrix A, and it's going to be zeros. And zeros is going to create a matrix of zeros. And if you just put one argument, what it will do is it will create a square matrix, a square matrix of zeros, you see? But if I want to create, for example, zeros, so let's call this A1, with a specific dimension. So, sorry, I want to have a zeros with one column, 3 rows. This is the way you do it, okay? One argument creates a square matrix, 3 by 3. If you have 2 arguments, it will create the dimensions that you want. Now, the same we can call B, as there are zeros, there are also ones, so it's the same idea. No, this is another special matrix. What we can also do is basically the identity matrix is another one that is important. Let's call this C. And to find the identity matrix, guys, or create an identity matrix, you simply do I. Remember that the identity matrix is that one that has ones in the main diagonal and 0 otherwise. Remember that if you want to get the elements of the main diagonal, you simply do a diagonal of C, and then you get all the elements of C, okay? Well, some basic matrix operations. So let's call A, for example, and let's call B, and let's say, okay, so we have A and we have B. So we have A and B there. And of course, the basic matrix operations, guys, in this case, we need to be sure that we satisfy the dimension conditions, okay? If you want to sum 2 matrices, okay, let's do this first. Let's do some explanation about the matrix operations. Okay, so if you want to sum A plus B, necessarily the number of columns, the number of rows and columns of A must be exactly the same as the number of rows and columns of B. But the same happens for plus minus. Now, if you want to multiply, okay, here, if we have n times m, this one must be n times p. So these two must be equal. Number of columns of A must be equal to the number of rows of B. And the resulting matrix, guys, so let's call this equal C. C is going to be equal to m times p. Right? So these are the crucial considerations here. Yeah, okay, so let's go back to Matlab. So what I can do here is I can do D equals A plus B. Here we go. E can be A minus B. Here we go. And F can be A times B, and they are conformable, so no big issue. Now you need to remember, guys, that A times B in algebra is completely different than B times A. Okay, so you just take a look to what happens if I simply reverse. It's not like scalars. Remember that 3 times 6 is the same as 6 and 3. In matrix algebra, this is not anymore the case. So if I change now B times A, you can see the product is completely different. Now, what you can do also is, of course, you can divide A divided by B. Here we go. What else we can do here? Yeah, of course, as usual, guys, there is this element by element operation. So we have done this already. So element by element operation. Well, in the case of the sum, it's going to be exactly the same. Oh, not sum. The sum, there's no element by element, I mean. So we have the product. So, and you can see element by element implies that first row, and so first element with first element, second element with second element, third element, etc. Okay, so it doesn't follow the multiplication rules of matrix. This is element by element. Element by element multiplication. You can do the same element by element division. You can also do the power, element by element power. Okay, So these are basically the common things here. Now, let's create a matrix I. Yeah, let's create I, and let's do this an identity matrix, dimension 2. One of the properties of the identity matrix, guys, is works more or less like the number 1 in a scalar. So if you multiply any number by 1, is the same number. So for example, if we do, let's do A times I, is the same A matrix. And what is interesting, guys, here is that if you reverse the order here, you obtain the same. So this is one condition that holds always for matrices. Now, there is another thing that we use a lot in econometrics. So let's call U, for example. Let's define this as a vector of errors, okay? Let's do 1, 2, 3. Okay, this is a common vector. So this is my U. All right? So if I do, U is a 4 times 1. Right? If I multiply, if I do this, U times U prime. Oh, by the way, U prime is a transpose. So it simply changes the columns into rows. Right? So if I simply multiply U times U prime, I can do that, right? U is a 4 times 1, and U prime is a 1 times 4. So the resulting matrix is going to be a 4 times 4. Okay? So this is the square of a matrix. Now, what is interesting is what happens if I do the reverse. I do U prime times U. So U prime is going to be 1 times 4. The other one is going to be 4 times 1. So the result is a 1 number. Okay? Take a look at that one. So 30. So this is a scalar product. This one here is called a scalar product. Okay, so yeah, what is interesting also about this one here, guys, U prime, sorry, U times U prime, all these elements in the main diagonal corresponds to the square of these numbers here. You see, 4 squared, 16, 3 squared, 9, 2 squared, 4, 1 squared, 5. Got it? Yeah, let's talk a little about the determinant. Just to remember what is the determinant and why the determinant is important. Yeah, I'm pretty sure you have seen this long time ago, or perhaps in your linear algebra classes or in some economic classes. So the determinant, guys, is simply, so let's do one example. If I do 3, 2, 1, 4, 6, 0, 1, 3, 1, for example. This is my matrix A, and what I want is to find the determinant of A. So remember, it was multiplying down, so multiply 3 times 6 times 1. And what normally we do to find this one here, we replicate the first and second column. Let me delete this part here. So the way we write determinant of A, we normally write A like that, like in absolute value, but also we use the word determinant of A. So, and this is going to be equal to 3 times 6 times 1 is 18. Then we multiply 4 times 3 times 1, 12. And then finally 1 times 2 times 0, that is 0. And then we subtract the elements going up. So when we go up, what we do is, well, this one here, I need to be careful. So it's going to be 1 times 6 times 1 is 6. Plus 3 times 3 times 0 is 0. Plus 4 times 2 times 1, so it is 8. Okay, so what do we have here? 30. So we will have here 30 minus 14 equals 16. So this is your determinant. Okay, and we're going to see a lot of properties of the determinant just using Excel. So let me show you. Not Excel, sorry, Matlab. So let's create a matrix. Okay, let's create a normal matrix A that is going to be also W1, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So this is your matrix, okay? And if we want to find the determinant of A, we simply, in the Matlab command is det, determinant of A. Okay, let me write this in a different way. So this number here, guys, is 0. Okay, we're gonna see what is the meaning of 0, determinant equals 0 in just a couple of minutes. Okay, so let me write another matrix then. I will change this one here. I will do 2, 1, 3, 4, 5, 6. Yeah, let's just change this number here and then we can compute the determinant of A. Okay. So if this is my matrix, when I do the determinant of this number, I get -9. Right? Some properties of the determinant, guys, is that the determinant of A, so the determinant of A, this one, 9, is going to be equal to the determinant of its transpose. Take a look. It's exactly the same. So the determinant of A equals to the determinant of the transpose. Okay, now what happens is the following. If I change one row or column, what is going to happen is that the determinant is going to be exactly the same, the number, but the sign is going to change. So for example, guys, I will create a matrix, another matrix, let's call it A1. Okay. And an A1 is going to be simply, where's this one here? No, all the elements of A or rows, and I want to change 2 minus 1, 2 minus 1 to 1. So this is going to be the first component. So I'm shifting the columns. And then I will simply add all comma 3. So what I'm shifting is the first position. Do you agree? If you see your A is 247, now 247 is in the middle. So what I've done is I have shifted the second column. Now, if you find the determinant of A1, you see, what happens is that the magnitude is the same, but the sign changes. Now, what happens if we multiply one column? Okay, if we multiply one column for times a scalar. So, for example, what I will do is I will replace all the rows column number 1. Sorry. First row, all columns, and I will put this. I will simply multiply this number. Sorry, this column here, this row here times 5. Okay, so you see what I've done? I have simply multiplied the first row times 5. And then if you find that, oh, yeah, if you find the determinant of A1, oh no, what I've done here, sorry, is determinant of A. A is the one that I have changed. It's now 45. So basically means that if you multiply times 1, times a constant, one of the rows, simply the determinant gets multiplied by that number. Got it? Now, what happens if we multiply the whole matrix? So let me see, let me recover A again. Yeah, this is A. So what happens if I multiply, let's call this C. I multiply A times a scalar, let's say 5. I multiply everything by 5. Got it? So what happens when I multiply everything by 5 and then you do the determinant of C now? This number here is going to be simply equal to the number is going to be 5 to the power to the rank of C. Rank is simply the number of columns or rows linearly independent. We're going to talk in a minute. Okay, 5 to the rank of, so let's just be sure, 5 to the rank of C times the determinant of the original matrix. Here we go. Right, so it's going to be 5. If we want to see the rank of C, I'm pretty sure it is 3 linear independent vectors there. Oh, not rank like that. 3. So it is going to be 5 to the 3. What is 5? 5 is the number that I multiplied to all the elements here. So it's going to be 5 to the third, and then multiply by a normal determinant for the original determinant. That's it, I think. Now, the rank, I already discussed about the rank. The rank simply is the number of linear independent components or vectors in a matrix. If you have a full rank, it implies that the determinant is different from 0. So this means that the determinant is non-singular. Okay, so let me write that, because this is going to be crucial for the econometric side you are going to be developing. So let me write this. So the rank equals number of vectors of linearly independent vectors of a matrix. And basically, if a matrix has full rank, implies the determinant of a matrix A is different from 0. Okay, and this part here, guys, is going to be extremely important. Right now, let's do a very simple example that I'm pretty sure. A solution of system of equations. I'm pretty sure we have, just to show you what we are going to be dealing with, having a determinant different from 0. So this one here, by the way, guys, is called A, is called a non-singular matrix. Okay, so A is going to be a non-singular matrix. So remember this system of equations that we used to solve in high school. And I will write something like that. If 3x plus 2e equals 6, for example. And then I have another equation, 4y equals 12. And then what we try to do here is, remember, there is one method that we simply transform this into matrices, x and y, and equals 6 and 12. And so basically the solution of this one here is x and y equals 3, 2, 6, 4 to the power minus 1. So this is the inverse of this one here, times 6 times 12. Okay, so this part here is the inverse of a matrix. Okay, and let's see what is the inverse of a matrix in Matlab, and then we're going to come back here. So let's assume, so I have 3, 2, no, let's do another first. Let's do another example just to show you how the inverse works. So let's go back to my A. So this is my A. I will call this D, and D is going to be A to the power minus 1. This is the inverse, or if you prefer in Matlab, inverse of A. So it is indifferent. There are some of the properties, guys, that we need to tell you, we need to work with that, is that A times its inverse equals the identity matrix. You see that? A matrix times its inverse equals the identity matrix. And also, if you reverse this one here, so A to the minus 1 times A, it is also equal to the identity matrix. Another property that we have is that, take a look to this. So let me close this. A inverse of a matrix. Inverse of a matrix transposed. Okay, it equals, let me copy this one, equals the inverse of the transposed. Oh, I've done something wrong. Not this really problem. You see, they are the same. So basically what I'm telling to you here, guys, is that the inverse and then you transpose is exactly the same as transposing first and then taking the inverse. Got it? Now, what is important, guys, is that why that the inverse is so important. So let me show you back my whiteboard. Take a look to how do you solve the inverse, okay? The formula of the solution of the inverse is simply the adjusted matrix of A. I will call this matrix A, okay? So this is matrix A. Let's call this matrix A. Okay, the inverse of a matrix, so A to the power -1, is simply that the adjunct of this matrix divided by the determinant of the matrix. Now, what happens if the elements of A, if A is not linear dependent? Linearly dependent. Sorry. It is linear dependent. What is going to happen is what? Basically, the determinant of A is going to be equal to 0. Remember, how do we call those matrices that have a determinant different from 0? This is like that parenthesis. When they are not different from 0, they are not singular. When the determinant of A equals 0, this matrix here is called a singular matrix. And the problem with singular matrix is the determinant equals 0. And 1 second, please. And what is problematic, guys, is that, remember that if the determinant is 0, what happens with the inverse of the matrix is going to be non-defined. If the inverse of the matrix is non-defined, what happens with the solution x and y is going to be simply infinite possible solutions. Right? So that's the main issue. Now, in your fourth assignment, guys, what you are going to be requested is to work with the OLS model. So I'm pretty sure you have all taken the ordinary least squares model, that the simplest model in regression analysis. And indeed, there, in order to find the coefficients, the formula is this one here, x prime x to the -1 times x prime y. So we are going to be concerned about the determinant of x prime x. Okay? So if x times x has linear dependency, so the determinant is going to be singular, and this solution is not going to be able to be obtained. A unique solution is not going to be feasible to obtain. So that's the issue, okay? And this is going to be part of your assignment number 4. Okay, so let's do a system of equations. Let's understand how a system of equations work in Matlab. So let's assume, guys, that I have, let's create first an example that we can replicate in. Let's create the following example. So imagine, guys, that we have x1 plus 2x2 plus 3x3 equals 366. 4x1 plus 5x2 plus 6x3 equals 804. And then we have another system of 7x1, another equation, plus 8x2 plus 9x3 equals 351. Okay, so we want to form first one here. We want to transform this one here into a matrix form. So we want this to be AX equals B. So A is going to be simply 1, 2, 3, the one that we have been working, 4, 5, 6. No, sorry, 1, 2, 3. Yeah, 4, 5, 6. 7, 8, and 9. This is going to be my A. My X is going to be X1, X2, X3. And my B is going to be 3, 6, 6, 0, 4, and 3, 5, 1. Okay, so this is my matrix. And that's the way what we need to do. So let's meet this, let's write this matrix here. Oh, sorry, guys. Sorry. Yeah, I will have a singular matrix. So I don't want to use the singular matrix example now. So let's assume that this one here is 7, 8, and 0. So let's replace this 1 by 0. Okay, so we'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. Okay, just to make it not singular. Otherwise, we're going to have problems with singularity immediately. Not the case at this point. So A is going to be 1, 2, 3, 4, 5, 6, 7, 8, and 0. So this is my A. Okay, what is going to be my B? My B is going to be, we said 366, we said 804, and we said 351, and I will transpose this one. So then I have A and B. And so what is the solution of my system? Remember, the solution of your system in this example is going to be, if I call this A, yeah, we know this is A, this is X, and this is B. So X is simply going to be A to the minus 1 times B. Right? And so that's what we are going to be building up in our simple example in Matlab. Just to see if we have a problem with our determinant, let's take a look to the determinant. Sorry. So my determinant is larger than 0, it's different from 0, so I have no issue with finding the inverse of a matrix. Right? So now what we can do is we can see simply my X is going to be equal to the inverse of A times B. Here we go with my solutions. So the values that satisfy these equations, these 3 equations, this is a 3 by 3 system of the 3 equations system. So it is X, 25, 22, and 99. Okay. Now, I will show you one M file that you need to replicate while you study this one here. Let me open one file. Will be called, it's a toy example also that you need to replicate. My system, this one here. Okay, so basically what I want, this is the one. No, this isn't the one. And let me open my one. No, simple one. Where is my system equation? Give me 1 second. I think I don't have it here. Yes, this one here. Okay, so this is my system of equations. So what it will do is it will solve what we have done. We are going to provide a system A and B. So this is going to be my matrix and the values of each equation. And then this equation, this function is going to solve our problem. So remember what I've done here is a couple of tests, just a dummy test. What I do is N is size of number of rows of A, number of columns of A. Then what I say is I have less than 2 arguments. If I have not A and not B, I will simply send an error. You need an input. You need to input A and B. So in order to have a system of equations, you need to have A, the matrix, and B. So if you have one of them, you cannot solve the system. Okay? The other thing that is important here, guys, is that my matrix A, just for making okay, so and also another test, I want A to be a square matrix. So that's why N, if N is not equal to M, so the number of rows is not equal to the number of columns, simply I send an error message, you know what, A is not a square. And I want to be sure also that B is a column vector. Remember, it needs to be a column vector is like this one here that we have here, B needs to be a column vector like that. Okay, just to be sure that we have a column vector, we can also test another thing is that we say that if size of B two, so this is the number of columns, is not equal to 1. So this implies basically that I don't have I have a row column instead of a row vector instead of a column vector, so I simply transpose it, okay, just to be sure that it works. Then I do the singularity condition. I say D equals determinant of A, and then we can see if determinant of, if D, that is the determinant of A, is 0, then we say matrix is singular. Got it? Otherwise, I simply create X is going to be the inverse of A times B, or another way that is more efficient, guys, in Matlab uses this A backslash B. That's exactly the same, but the mathematics are much simpler. Okay, the mathematics involved are much simpler. Okay, so what we can do now is, I remember, as we always call our system, so our solution, let's call this one here. I have A, I have B, so I should be able to obtain this. Here we go with my solution. The same solution as before. Okay. Now, what do you remember? We were talking about a system that was yeah. Let's go back to this example. So let's try to do this. A is going to be 3, 2, 6, 4, and 6, 12. Okay, let me take a picture here so you can. Oh, 3, 3, 2, 6, 12. Yeah. Let's try to solve this equation now. So now let's tell A is what was that? 3, 2, 6, 4, and B was equal to 6, 12. I just write in semicolon to have it immediately later. You see? Now let's try to run our program again, the program that we have computed here. And here's we have the system. You see that? Error using this, matrix A is singular. You can see here. So what happens is that if you take the determinant of A, what happens is 0. So you cannot solve this equation. You're going to have infinite solutions. So that's why it's so important, guys, to you understand the singularity, non-singularity, and why this is important. Okay. So you need to redo this program just to understand how this program works, etc. Okay. Yeah, I think we can move here. Yes. Okay. So now let's go into a special, into some of the special, matrices or transformations that are common in linear algebra. So let's define X, for example, guys, to be equal to 1, 2, just another toy, 3, 4. Okay. So now let's create this matrix, and then what we are going to create is something that is called the norm. Okay, so this is the distance between the elements of X. So what I will do is norm X, and the ones that we normally use is the Frobenius distance. So this is the norm, it's 5.47. Just as a matter of exercise, what we can do is let's create a program that computes our Frobenius, okay? So the Frobenius, the norm is simply the Frobenius norm. Is simply, guys, the square root of the sum of the let me write better, not to confuse you. Simply going to be the sum, okay, of the diagonal elements of X prime X. Okay, so this is my Frobenius. So in order to get in Excel, remember, this is very simple. It's simply norm. We say X, and then Fro comes from Frobenius, and then you get the number. But indeed, what we are going to be doing is creating this one here. Okay, we're going to create the formula. So let me share this Matlab. Okay, and we'll open another file that you need to replicate. How is it called? Yeah, my Frobenius. Easy name. My Frobenius, here we go. Okay, so what I want to return is this is the Matlab norm, and this is my created norm. Okay, and I call it my Frobenius. I want simply a matrix X, and what it does is this one. What I told you is a square root of sum of diagonal of x prime x. So what is the first thing we need to compute, guys? Is we need to compute x prime x. So what I call here is x aux is simply equal to x prime x. So I'm computing this part here. Okay, then what I do is I take the diagonal elements of this matrix here. So it's diagonal of x auxiliary. I call this dx auxiliary. And then what I do is I simply sum. So I take, these are numbers. So why don't we do this? Let's do this. Let's do this because I have x here, right? Yes. Then what I do here, x prime x is this one here. Then what I do is I take the diagonal of these elements, so 10 and 20, basically, you see. And then what I do is I sum these elements of the diagonal. And I have 30, of course, 30. And then we have the sum of the diagonal of x prime x. And then what I need to do is simply take the square root of this. So simply the square root of this is the sqrt, is the command. Enter. No. Why sqr? It is sqrt. Here we go. 5.4772. And if you do, guys, your norm Matlab, so your Frobenius that is built in Matlab, you obtain the same number. Okay. So this is also another exercise just to get familiar with M files that we're going to be working more frequently, guys. Okay, another linear algebra command that we need to use as a transformation is the eigenvalues. Okay, so let's define where is my A, the one that we define for example of the system. Yeah, let's define this A. Okay, so this is my A. So if you do, for example, guys, let's take a look to D and let's call this eigenvalues of A. Apparently the numbers are, what are these numbers? Why they are useful? Okay. However, these three numbers, guys, satisfy three properties. The first of them is the following. Just compute T, okay? And let's compute the trace of A. So the trace, guys, is simply the sum of the elements of the main diagonal. Take a look. The main diagonal, you sum 6. Got it? Now, what if you sum D? You see? So remember, D corresponds to the eigenvalues of A. So first property, the sum of the eigenvalues equals the trace. Right? The second property is the following. The number of eigenvalues different from 0 equals the rank. So in this case, how many eigenvalues do we have different from 0? 3. So the rank of A should be equal to 3. And this one here is crucial, guys, because the number that if we have full rank, remember that we have an invertible, non-singular matrix. So this implies that the determinant is different from 0. This implies that the inverse of a matrix exists. Right? So this is a second property. The number of eigenvalues different from 0 are simply equal to the trace. And finally, guys, the product, I will call this DD, the product of the eigenvalues equals the determinant. So if you take the determinant of A, you get this one. Okay, so you have three properties with the eigenvalues. Now, there is another property that, let me write this first here. There are a couple of properties that are really interesting. You're going to see this later. So eigenvalues. There are a couple of properties. There is one property that tells basically this is if this is A my matrix, I multiply times B, this is going to be equal to B times D. All right, so let's compute first A and D. So when you do this in Matlab, this is going to be simply, let's call this B and D. And this is going to be simply eigenvalue of A. Okay, so B is going to be this vector, and D is going to be my eigenvalues organized in a matrix way. So let's take a look at this. It's very, very easy. So I have this one here. So what I will do is I will add one element, one additional output, B and D. You see? So B is my eigenvectors, and these are my eigenvalues. These numbers here, guys, are exactly the same as the ones that we have in here, but organized in a diagonal way. Right? Now, what is interesting is that if you multiply A times B, and then you multiply B times D, you obtain the exact same property. Got it? So this is one of the properties of the eigenvalues, eigendecomposition. So now let's take a look to, there's another one just for practice. If I do the following, let me check. Oh, yeah, let me check. And because from here you're gonna see what something interesting happens. From here, A times B equals B times D. I can do A times B minus B times D, correct? And what I will do is I will do B minus 1, so I will do this artificially. So I will multiply this times B, okay, B minus 1 times B. So remember that B minus 1, any matrix to the minus 1 times the matrix is equal to I. So I'm not changing anything. And this equals 0, correct? Because I'm moving this to the left. And then here, guys, A minus B, D, B minus 1 that multiplied by B, that multiplies B, is going to be equal to 0. Okay? So let's take a look at that. So A minus B, D, B minus 1, B equals 0. So let's do this in Matlab, and let's verify that this works in Matlab. So I will do A minus B times D times inverse of B, all this times B, something like that, gives us, remember, it looks like numbers, but indeed it's e to the minus 14, so it's 10 to the minus 14. So these numbers are technically equal to 0. Right? Now we go into something that is called the eigendecomposition, guys. And the eigendecomposition tells us, and this is one of the things that I find very, very useful when we work with matrices, the eigendecomposition. I will write this here. Okay, and the eigendecomposition tells us the following. So I will start again. Where's my? I will start again with AB equals BD. Okay. What I will do here is I will do AB multiplied by B minus 1. And in order not to change anything, what I will do is B minus 1 here. So you know that this is I, identity matrix. So this is A equals B, D, B minus 1. Right? So this is crucial. This is, you're going to see how beautiful is this one here. Okay. Now, what is interesting, guys, is that with this equation here, what you can do is you can find whatever you want. So you can find, for example, A squared. So A squared is going to be B, D, B minus 1, multiplied twice, right? B, D, B minus 1. So if we multiply this one here, we have B, D, B minus 1 times B, D, B minus 1. So this is I, and this is going to be B, D squared. Remember, D is a diagonal matrix. So when you multiply two diagonal matrices, it's simply D squared. And that D and D is D squared times B to the minus 1. And so this is your A squared, guys. Okay, so we can generalize this one here, and then we can argue that A to the n is simply B, B to the n, B to the minus 1. Okay. So we can try to do that. Okay, so let's try to do that. Where I do this? Yeah, let's do a new share. Let's do a new share. So let's first compute, be sure that we have B, times D times inverse of B equals A. You see, this is A. If you take a look to our matrix A, 1, 2, 3, 4, 5, 6, 7, 8, and 0. So this is satisfied. Now, if I want to find A2, I say A squared, it's going to be simply B times D squared. So I will put this just in parentheses just to not confuse myself, times inverse of B. So this is your how do you call it? A squared. It's not a square in each individual number, as you see, guys. It is not like that. It's a matrix multiplication. So that's why the eigen decomposition, guys, is so powerful, so beautiful. And you can see, you know, this is A times A. Indeed, is this one here, you see? Okay, so it's the power of a matrix. Now, also, of course, you know, if this general formula applies in this case, also what we can show, guys, is that A to the minus 1 equals B, D to the minus 1, E to the minus 1. This is extremely beautiful, guys, because D is a diagonal matrix. So you can simply, if you have in the diagonal, imagine if you have 1, 5, 0, the DL minus 1 is 1 over 1, 1 over 5, well, 1 over 0, so you have identified here. But we can try and let's take a look to if this works here. How the eigenvalue decomposition also helps us to find inverses in a much quicker way, much quicker way. So let's call this one as let's not equal. So let's do B times inverse of D times inverse of E. What I've done. Oh, I don't run something wrong. Yeah, I can put this here. No, it's not in, it's in. Here we go. And take a look to the A to the power minus 1. It's exactly the same. It has, you know, if you have a 3 by 3, of course, for Matlab, doing the regular A to the minus 1 is piece of cake. It's has almost the same time as having the eigen decomposition formula. But if you have a huge matrix, guys, you know, imagine that you have a, 100,000 rows times 25 columns, trying to, say 250 times 250 matrix, and you want to find the inverse of this matrix, it will take a lot of time and resources in Matlab. However, if you do first the decomposition, then it's a very simple transformation of the data, and then you apply this formula here, piece of cake. Because here the inverse is of a diagonal. Remember, D is a diagonal. You see, now if you take the inverse of D, what is this number? It's simply 1 divided by 12. What is this number here? It's 1 divided by 0.38. And what is this number here? It's simply 1 divided by this. Right? So it's extremely simple and extremely efficient in the use of times. Okay. Another decomposition that we normally use, guys, is what is called a singular value decomposition. So, and I will show you the properties. In Matlab, simply let's call this US. So these are the parameters of these returns, and singular value decomposition, and let's do of A. Okay, and then you obtain this one here. What is interesting, guys, is that A is simply equal to USB. U times S times B. Take a look. So you can recover the matrix as before. Oh, sorry. No, this is not correct. USB prime. Yes, otherwise you don't transform this one, you don't have the transformation. Okay, so, and with this one here, guys, I think that we have done, we have basically what we need from linear algebra applied into Matlab, and then you can use this learning, what you have learned in this class, to do basically assignment number 4. So let me show you assignment number 4. I think it's assignment number 4. Yes, okay, so let me let me show you assignment number 4. I will also give this to you. I will send this to you. Okay, so up to assignment number 3 are going to be due on Monday. I'm talking about Monday 14th. Okay, assignment number 4 is going to be, I'm pretty sure that you can do on the 16th, for the 16th. Okay, so that first assignment, guys, simply tells you how to do it. The number 1 is optional. Let's focus on the find the inverse of a matrix using an eigendecomposition. We have done that. Using the eigendecomposition, find a square root of a matrix. Now, and then you create a very simple matrix that can sum element by element multiplication and power, matrix multiplication, inverse, etc. And then you need to do this starting from this M file. You are going to do a bunch of other requests. Okay. And then you have 8 programs there are very simple to understand. You need to understand the transpose example, how this works, and do a more generic program, and you are going to create your own program that's going to be able to create transpose of matrices. Okay, guys, I will send you the information right away. I will post this video as soon as possible, and then we continue in class with, we start now with loops. So I prefer to do that, during class. Okay, guys, see you later.